Welcome to RoRe Academy YouTube channel 2.0. Our new and improved channel is dedicated to showing you how things are put together, from concept to prototype. If you're into EVs or work with electric cars, you need to check this out. The Automotive Ultra EV Diagnostic Scanner is seriously one of the best tools out there for deep dive battery diagnostics and full system testing on electric and hybrid vehicles. It's fast, accurate, and super easy to use. Honestly, a total game changer if you're serious about understanding your EV inside and out. So if you want to grab yours, just click the link in the video description below and check it out. In part 3 of our BYD Seal Power Domain Controller Teardown series, we shift our focus to the onboard charger, taking a closer look at its structure, layout, and integration within the PDC. The onboard charger plays a critical role in converting AC grid power into regulated DC energy for battery charging. In the BYD Seal, this function is fully integrated into the power domain controller, contributing to the system's high level of power density and functional consolidation. In this section, we'll examine how the onboard charger is partitioned mechanically and electrically, including the power stage arrangement, control and gate drive circuitry, isolation boundaries, and thermal interfaces. We'll also look at how the charger interfaces with the AC charging input, high-voltage battery system, cooling loop, and vehicle communication networks, and how these connections influence efficiency, EMI performance, and serviceability. By understanding the onboard charger structure, we can better appreciate the engineering trade-offs BYD has made between integration, performance, and thermal management. Let's start by breaking down the physical architecture of the onboard charger inside the PDC. One of the key highlights of the BYD Seal is its highly integrated electric drive unit, or EDU. This EDU brings together 8 major subsystems into a compact, vehicle-level powertrain architecture, designed to improve efficiency, reduce cabling, and simplify system integration. At the heart of this EDU is the Powertrain Domain Controller, or PDC, which alone integrates 6 critical power electronics and control functions. First is the motor control unit, or traction inverter. This inverter delivers up to 230 kilowatts of peak power and is built using silicon carbide MOSFET technology. The use of SiC devices enables higher switching frequencies, reduced losses, and improved thermal performance. In this architecture, the inverter operates alongside the e-motor to support the transition from a 400-volt battery system toward an effective 800-volt drive capability, improving efficiency during high-power operation. Next is the onboard charger. The BYD Seal supports 11 kilowatts of AC charging and up to 150 kilowatts of DC fast charging. The system also enables vehicle-to-load functionality, delivering up to 3 kilowatts to external loads, turning the vehicle into a mobile power source. The third component is the power distribution unit. This manages high-voltage power routing between the charging port, traction inverter, e-motor, and high-voltage battery pack, acting as the electrical backbone of the vehicle's high-voltage system. The fourth element is the DC/DC converter, responsible for stepping down high-voltage battery power to support the vehicle's low-voltage electrical systems, ensuring stable operation of auxiliaries and control electronics. Integrated alongside this is the battery management system. The BMS continuously monitors cell voltages, temperatures, and currents, ensuring safe operation, optimal performance, and battery longevity. Finally, the vehicle control unit coordinates all of these subsystems. It manages torque requests, energy flow, charging modes, and safety functions, effectively acting as the supervisory brain of the entire powertrain. Outside the PDC, the EDU also incorporates the electric motor and gearbox, completing a tightly integrated drive unit designed for high efficiency, high power density, and reduced system complexity. This level of integration represents a significant shift in modern EV powertrain design, and in this video we'll break down exactly how BYD has engineered it. We focus on the onboard charger in this video. Let's take a quick system-level view of the Powertrain Domain Controller, focusing specifically on the top and bottom sections and the external connection points, without diving into internal circuitry just yet. Starting with the topmost section of the PDC, this is where most of the high-level interfaces are located. Here, we can see the high-voltage battery connection, which links the PDC directly to the vehicle's main battery pack and serves as the primary energy input for the entire powertrain. Adjacent to this are the coolant connections, which form part of the thermal management loop. These interfaces allow heat to be extracted from high-power components such as the inverter, DC/DC converter, and onboard charger. We also see the DC fast charging connection, which routes high-power DC energy directly into the system during rapid charging events, bypassing the onboard AC charger. Alongside this is the AC charging connection, used during conventional AC charging, where the onboard charger inside the PDC processes grid power. Moving to the low-voltage interfaces, the 12-volt connection supplies power to vehicle auxiliaries and control systems, typically via the internal DC/DC converter. Finally, the communication connections are located here as well. These interfaces handle data exchange between the PDC and the rest of the vehicle, enabling control, diagnostics, and safety monitoring. Now, shifting to the bottom section of the powertrain domain controller, we primarily see the e-motor connection. This is the high-power three-phase output from the traction inverter, delivering controlled electrical energy directly to the electric motor. In this section of the video, we disassemble the onboard charger and DC-DC converter power board, revealing its modular internal structure. The assembly is divided into 4 distinct subboards, each serving a specific function within the power conversion system. The first subboard handles the onboard charger control, managing charging logic and communication. The second subboard is dedicated to electromagnetic interference, or EMI mitigation, ensuring compliance with automotive EMC requirements. The third subboard provides the low-voltage power supply, supporting auxiliary electronics and control circuits. And the fourth subboard is responsible for DC-DC converter control, regulating high-voltage to low-voltage power conversion. This modular design improves serviceability, noise control, and functional isolation, while supporting high efficiency and reliable operation. Thank you so much for watching today's video and exploring how the onboard charger of the BYD Seal is put together, while highlighting its critical hardware components. Remember, here at RoRe Academy YouTube channel 2.0, you watch, learn, and understand how to prototype. See you in the next video. If you found this video insightful, don't forget to like, subscribe, turn on notifications, comment, and share, so you never miss our next deep dive into the world of technology and innovation.